Thank you, Stefan. Thank you, Didier. Stefan, Didier said he'd lost a little bit of hair since he arrived here in 2007, sorry. I arrived in 2004, and I think I've got a few more grey hairs since then. But I can promise you it's got nothing to do with my wonderful job here at Airbus. Ladies and gentlemen, firstly I'd like to add my warm welcome to that of Thierry and Didier this afternoon. I'm sure that you've all felt the buzz of excitement and eager anticipation that on your arrival here that flows around the site here at Airbus. The enthusiasm and the dedication which pervades through all the teams involved in the aircraft design and preparation is certainly infectious. For all of us involved in the flight testing of this marvellous new machine, we're extremely privileged to be so closely associated with such a project which has been developed by such a great team of engineers and specialists over many years. And it will be presented, of course, to you as the beautiful aircraft that you will see tomorrow afternoon close up. It's often said that if an aircraft looks right, it flies right. And boy, does this aircraft look right. You'll see tomorrow. The proof, of course, will be in the flight testing, but I can assure you that we have a high level of confidence as we move closer to first flight. Within the Flight Test and Integration Centre, we are very much looking forward to taking the aircraft to the next phase of the A350 adventure, the flight test program itself. This afternoon, I'd like to take 30 minutes or so of your time to describe the program, what it consists of, and how we're intending to take the aircraft from first flight to certification in a record time for us of just over a year. It'll certainly be a challenge, as Didier said, but the planning and the mitigation which has gone into the program design leaves us confident that provided we have no major surprises along the way, we should be delivering our first 350 XWB in the latter half of next year. But before we take a look at the flight test program and the first flight itself, it's important to understand the significance of the months of testing of Aircraft Zero systems and test rigs which have gone before. As Didier mentioned, the concept was to try and front-load as much of the developmental testing in as representative an operating environment as possible. This approach has always been taken to a certain extent, but we've pushed it even harder with the A350 in order to establish a high level of maturity before moving forward. It has two benefits. Firstly, we de-risk the program in terms of surprises, which may require time to fix, and whether it's hardware or software. And secondly, along with the novelty of having 5 aircraft now running in parallel, we increase the efficiency in terms of program length, which should run to around about 2,500 hours of flight time and a little over 12 months. So it's a quite aggressive program. So let's look at these preparatory test programs. The flight test bed, as Didier mentioned, first flew beginning of 2012 with the Trent XWB engine. And the results that we achieved in partnership with Rolls-Royce were extremely pleasing, and it gives us great confidence in the power plant as we move towards first flight. As is best practice in flight tests, we have to carefully manage risk, and therefore we try and avoid flying a new engine-airframe combination where we can. So we always try and use a flight test bed to develop the confidence in the new power plant. With the large number of hours that we now have for running the Trent XWB engine on both the A380 and of course on the test benches in Derby with Rolls-Royce, we now have one less concern as we approach the beginning of our flight test program. In March of 2012, we started work on landing gear 0 at the facility in Filton in the UK, and this also provided confidence in the mechanical functioning and hydraulic systems associated with the new double-side stay landing gear design. The one part of the equation, of course, that we're unable to produce here is the aerodynamic loading and some of the aeroelastic effects, which are only modelled at this stage, but these variables we can confirm later in flight test. However, many hours of extensions and retractions have been carried out to ensure the reliability of this system when we go for first flight. High Lift Zero, the high lift rig at Bremen in Germany, is an exact copy of the aircraft flap and slat system with their complex mechanical arrangements for providing differential flap operation and variable camber using the adaptive drop hinge flap system. This is a very complex mechanical system, and so we need a high level of reliability before flight. So this rig has been essential, not only as a great confidence builder for us, but also for maturing the systems themselves. The virtual first flights that Didier mentioned, basically the simulator that we use, the aircraft simulator, is the closest that we can get to simulating the first flight while still on the ground. It's connected to the Iron Bird, the hydraulic rig that we have over in the simulation center, and with generators and load benches as required, so we can get as close as possible to simulating that first flight or any other flights that we need during the flight test process. It's with this simulator that we run through all the different failure cases and plan and practice for many of our test flights. It's the means to find and mitigate many issues that we would rather find in the safe setting of the simulator, of course, rather than in flight. As they say, one would rather be on the ground wishing one was in the air than in the air wishing one was on the ground. And finally, the Cabin Zero in Hamburg, a true representation of the cabin and all its associated systems, which gives us a complete end-to-end possibility of checking the cabin, such as the cabin systems such as the galley, crew rest, water, waste, etc. And in July, we planned the cabin virtual first flight with a full complement of passengers and crew, just to make sure everything works in a simulated flight from start to finish. So, just to give you an idea of the extent of the testing that we have gone through over the last few months in these aircraft zero test beams, we've got about 3,000 hours on the Iron Bird hydraulic rig, with about the same on the aircraft zero simulators, of which we have 2. 3,800 hours approximately on the high lift systems, 860 hours on the Cabin Zero, and we're now approaching 300 hours on the flight test bed. And that's not forgetting the many hours, of course, that Rolls have put into the Trent XWB on the ground at Derby. The landing gear and the zero fuel, the fuel rig Zero at Filton account for another approximately 2,500 hours of preparatory test work. So at the end of the day, you can see that the earlier we can actually identify the issues, the simpler and quicker the fix in general, the more mature going into flight test, and the more confident we can be as we move forward. It's never guaranteed, but it gives us a much greater chance of success. So before discussing the test program, what I'd like to do is to give you a quick reminder of who is on board during a typical flight test, as we operate slightly differently to our transatlantic cousins. The crew are, of course, just the front end of a much larger team if we include all the backup specialists in the telemetry room, chase aircraft, ATC, all the players involved in these flight tests. However, the onboard team for the first flight consists of 6 people. 2 pilots, a test flight engineer, and 3 flight test engineers. I will explain. It's typical of our operations to have a certain number of flight test engineers down the back to effectively run the flight test profile. They basically plan the profile and they direct it from the back. And they vary from day to day depending on the particular test requirement for the aircraft. The pilots flying the first aircraft have been implicated in the operational side of the cockpit and systems design for many years now, as have quite a few of us within the flight test team. The test flight engineer, he has a very special role because he tracks the prototype really from its birth. So from when it was in the FAL, starting to come together, he is following it through, and he is responsible really to let us know what the state of the modifications and limitations are for that aircraft. So that for every flight, we know exactly the status of the aircraft going into it. In the case of MSN1, Pascal Vernet will be performing this task, and he will follow the aircraft right the way through to certification. Fernando Alonso and Patrick Duché will run the first flight test profile as flight test director and assistant, and they'll be aided by Emanuele Costanzo, another flight test engineer, who is an engine specialist, and he'll be monitoring the Trent XWBs throughout. He's been managing the flight test bed program over the last year, so he's very familiar with working with Rolls-Royce and working with the Trent XWB. MSN1 is now being prepared, as you know, out on the flight line. Systems are being checked and flight test instrumentation verified. And of course, it's only once we're completely happy with the technical state of the prototype will we go for first flight. And I'm sure you'll hear more of that over the next few days. So, program overview. In general terms, the flight test of a new commercial aircraft follows a relatively standard pattern. However, there are some differences for the A350 XWB. Firstly, as with all other test programs, we have a very short period of aircraft identification. If you take the lower line on this slide, the initial development period, really, initially we have to understand what we have to start with. So we go through an identification phase which encompasses the first several flights, really to understand where we are to start with. And it's only then can we start to develop forward. We try and make an aerodynamic freeze relatively early on because it's important that we have that aerodynamic configuration frozen in order to truly assess handling qualities and performance. And so it's important to try and push that to the front of the program within reason. And then systems and the rest of the aircraft develops as we move through the program. We get to a point where we start to collaborate with the certification authorities, and it's important at that stage that whatever we happen to be running through a certification test is in the final certification standard. So as we move through the development phase, certain parts of the aircraft will mature to a point at which we feel they're right for certification. We try and phase advance as much of the certification testing as we can because it's quite a complex process and there's a lot of paperwork behind that process in terms of the authorities. So it's important that we don't leave it all to the last minute. However, there are certain aspects of the certification which we can only do at the end once the final aircraft, total aircraft configuration is complete. So that's more or less the certification plan. But to achieve this in just over a year, we've obviously got to do something to really try and compress it. And we've done this by including the 5th aircraft. If you remember with the 380, we finished certification. We just had our 4th aircraft just prior to certification. So the first 2 aircraft that we will pick up, of course, MSN1 and MSN3, are both heavily instrumented. And they will do the bulk of the handling qualities, the systems and the loads testing, and of course Flutter. MSN2, the 3rd aircraft, will have a cabin and medium instrumentation fit and will be used for a trial at the McKinley Climatic Chamber at Eglin Air Force Base in Florida in a hangar where we can take the aircraft from -40 degrees to +50 degrees overnight if necessary. It's quite an impressive setup. MSN2 will also be used to carry passengers for the first time during the early long flights, similar to the early long flights that we did with the A380 in 2004. These flights will give us the first opportunity to, 2005 I should say for 380. These flights give us the first opportunity to see how the aircraft operates in this configuration with a full complement of passengers and crew. And therefore, the cabin zero virtual first flight is absolutely critical to the success of these flights. The 4th aircraft, MSN number 4, has a light FTI fit and will be destined primarily for noise measurements and avionics development. And finally, MSN 5, with a light instrumentation fit and a full cabin fit, will be used for ETOPS certification and the functional and reliability requirement, known colloquially as route proving. And this is the exercise where we have to prove to the authorities that the aircraft is really fit for purpose. It'll carry a full or close to full load of passengers around the world in a typical airline operation for a total of 300 hours. That's the requirement by the authorities for certification. It's also this aircraft which we will use to prepare some of the first instructors and crews for operations, as it's equally important that we have a cadre of trainers and instructors very early on in the process in order for a rapid introduction into service and ramp up with deliveries. So, all being well, we'll have the aircraft type certificate in the summer of next year, ready for first delivery in the latter half of next year. However, in order to give you a feel of some of the tests that we'll be performing during the course of the year, I have a few videos here that will show you what we did on the previous A380 program, of course, which we will have to do on A350 on the way towards certification. The first one that I'll show you this afternoon is the VMU testing. And this is important because VMU is the speed of minimum unstick. So it's the slowest speed that we can get airborne, basically the point at which the tail scrapes along the ground and the aeroplane gets airborne at effectively the maximum geometric angle attack that it can take on the takeoff run. The reason we need to know this is that when the pilots calculate their V-speeds, we want to make sure they don't bang the tail on the ground. So it's very important, if we have the reference speed, we can then calculate our V-speeds accordingly. So this little video clip gives you an idea of the test, what the test involves. It's a test that we don't like to carry out too often because at the speed we're getting airborne, there's the only possibility if an engine fails at the liftoff point is to close all the thrust levers and land back on the runway, because we're below the minimum control speed once in the air. But once the pilot's in the air, we'll bring the power up and accelerate so that we're back into a safe area again. The next one, the crosswind testing. Now this is quite interesting because from our modelling and simulations that we've done so far, we've had very good results for the A350 XWB in a simulated crosswind based on our aerodynamic models, etc. And we think we'll have at least as good performance as we had with the A380. The issue for us is that we have to demonstrate to the authorities the performance in a crosswind, and it's finding the crosswind. So for the 380, we finished up going all the way to Iceland, the 3-hour trog, to find somewhere where it's nice and windy. And this is the A380 performing in a 50+ knot crosswind, performing a takeoff here in Iceland, at Keflavik. They have two runways at 90 degrees, so whichever way the wind's blowing, there's always a crosswind. Most of the airline pilots wonder why we're using the runway that's not in service for the day. But it's a great place, it's just a shame it's so far away. Water trough test, another one of the more exciting tests that we have to do. Generally done down at Easter, where they've got a nice long runway and they have the facilities for setting up what we call here the piscine on the runway. The idea is to make sure that there are no issues with the engines ingesting water. When we run through the water at high speed, that there are no problems in terms of the brake units, hydraulic lines, and landing gear, in terms of the water plumes that are thrown up by the main gear and the nose gear. And you'll see in a minute when the aircraft is running down the runway the impressive effect that the water plumes have on the aircraft. So that's the piscine. This is the aircraft running down towards it, and there we go. So there's quite a lot of water force from the water being thrown up into the gear and down across the wings. And obviously you can see there it's not going down the engines at that point, which is good news. VMCG, a little bit about this. This is another one of those tests that all the pilots like to do, but it's quite, as the French say, sensible, but it's a little bit touchy. We have to be very careful. We have to practice a lot in the simulator before we go and do it, because there is a certain degree of risk involved. Basically, the idea, we have to demonstrate the minimum speed at which, with a critical engine failure on the runway at takeoff, the aircraft can be controlled to a 10-meter lateral deviation with aerodynamic means alone. So that means that we have to fail the critical engine by cutting the fuel off, physically cutting the fuel off to the engine at various speeds. And we start at high speed where the aerodynamic effects are great. and we get good control on the runway, and we gradually reduce the speed to a point at which we exceed the 10-meter deviation. Now, we mustn't come down in speed too far because we risk going off the side of the runway, so it's actually quite a tricky little test to do, but it's very interesting from a flying perspective. And you'll see on this one, you'll see the rudder come in and the aircraft deviate on the runway as the engine is shut down. It's also pretty hard on the engines because we're shutting the engine down from high power. It's obviously very hot internally, and we're suddenly switching off the fuel. So the engine, after several of these tests, has lost a lot of its life, shall we say. And then we get airborne. So that gives you a little bit of a flavour for what we have in store for the next year. But before I close, I think it's worth saying a little bit about the first flight itself. I don't want to say too much because I know many of you will be coming back here when eventually we announce the first flight, and I don't want to steal my thunder from the presentation that I give on that day. But in flight test, it's always, we always take an incremental approach in order to minimise risk, and it's no different really for the first flight. So the first flight has started very much in the middle of the envelope. Medium weight, medium CG, and we take everything nice and steadily, nice and incrementally. The aircraft is flown off the ground in the direct law, so we basically disconnect the higher order flight control systems, computers, and we fly it in a very much a stick to flight control surface relationship, so we can feel the pure aircraft as we get airborne. And we fly it up in the given configuration to a medium altitude around about 10,000 feet for the first part of the test, just to make sure the handling is okay, make sure everything's functioning as we would expect it, no surprises, we're not going too far out away, 200 knots is about where we go to on this particular part of the test. Once we're happy with the initial handling, we'll then look at some of the configuration changes for the flaps. That will be done nice and progressively. Once we're happy with the configuration changes, we'll then look at the gear retraction. And that will be done obviously with a chase aircraft. We've got telemetry, all the guys on the ground, all the specialists monitoring everything very closely. Once we've cleaned up, it's then time to start to think about putting in switching on the flight control computers. We'll have a look at the normal flight control law. We'll then push the speeds out. We'll do a little bit of aeroelastic work, looking at the natural response, aeroelastic response of the aircraft, to make sure that it's coming up as our predictions from the various tests that we've done on the ground and the various modelling of the aerodynamics and the structure that have gone before. We'll push the speed out to the high-speed end of the normal operating range before moving up to medium altitude, a slightly higher altitude, in fact 25,000 feet, another handling exercise, and then eventually when we're happy we'll go even higher to look at the high Mach, high altitude handling up at level 430. Once we're happy, we'll start to come back down to medium altitude where we'll start to prepare for our approach and arrival, just checking the approach configurations to make sure that we're happy to bring the aircraft back to Toulouse. Once everybody's satisfied, the aircraft will come back, it'll do, all being well, it'll do a flyby across the runway at around about 1,000 feet before turning downwind into position for the final landing. I trust that many of you will be able to join us on the day. I know that you've all made a big effort to come down here today, and I don't know when the first flight will be, but it's probably not too far in the future. So it's a big effort for you guys to come here twice. But I hope to see many of you on that day, whenever it happens to be. I also hope that I get the chance to chat to you over the next couple of days. I'll be here. I'll be taking you around the aircraft tomorrow. So feel free to come and grab me if you have any questions, after the question and answer session. I'll be more than happy to do the best I can to answer. Thank you very much for listening, ladies and gentlemen.